I'm going to hand over the presenter tools here to Bruce.
All right, thank you, Brenda. So in this section, I'm going to address hydric soil functions. So first, wetland functions. These are the biological and physical processes that occur in wetlands. The wetland functions are frequently classified as hydrologic, biogeochemical, or those functions that pertain to food webs and wildlife habitat. So this module is going to concentrate on wetland functions that are directly attributable to the soil component of wetlands, hydric soils. So John gave you a hydric soil definition. I think it's worth repeating. So hydric soil is a soil that formed under conditions of saturation, flooding, or ponding long enough during the growing season to develop anaerobic conditions in the upper part. And to repeat, anaerobic means free oxygen is absent, aerobic free oxygen is present. So these characteristics of water retention long enough close to the surface to develop anaerobic conditions, gives the hydric soils a unique capacity for some of the hydrologic and biogeochemical functions. Your hydric soil functional capacity is going to be dictated by landscape position and surface shape. These impact not only soil type, but also dictate the plant community and the rate at which water is going to move through that wetland. Let's go over a few definitions. A hydroperiod is a seasonal pattern of water table depth. Hydrodynamics refers to the energy and direction of water flow. And residence time is the time it takes for a given amount of water to enter, move through, and exit a wetland. Since chemical processes take time and are often in sequence, this residence time can determine whether or determine the capacity of this soil to remove pollutants from a water column. And since hydric soils differ in physical and chemical characteristics, the soil type is going to impact functional capacity. So a hydroperiod is the seasonal pattern of water table depth in a wetland. And here we have two hydroperiods, wetland A and wetland B. Wetland A, you can see that the water table stays within 6 inches of that soil surface for most of the year. Wetland B, we have a very dynamic water table, a lot of fluctuations. Water table is dropping and rising to a considerable extent. Now here's your take-home message. With respect to functions, not all wetlands are created equal. We shouldn't expect a permanently inundated cypress swamp to have the same functional capacity as a mineral soil flat. They'll have different hydrologic regimes, therefore different soil types, and different plant communities. One may excel at hydrologic functions, but be relatively poor at biogeochemical functions. Since hydrology drives these systems, let's start off with hydrologic functions. Hydric soils facilitate and regulate the flow of water between groundwater systems and surface water systems. This is the basis of hydrologic functions in these soils. To understand these functions, we need to be familiar with a few hydrologic definitions. Recharge is the movement of water from surface water to groundwater. Discharge is the release of groundwater to the soil surface. And base flow is the portion of stream flow that comes from subsurface flow. Our first function is going to be dealing with hydrodynamics, the energy and direction of water flow, and that function is energy dissipation. Some wetlands capture large volumes of stormwater runoff and overbank flow and release the water at a slower rate and therefore lower energy into other surface waters or into the groundwater system. And this reduction in velocity is going to promote sedimentation and infiltration. We appreciate the value of wetlands in reducing stormwater runoff. This is due in part to high infiltration capacity of hydric soils. Infiltration is the movement of precipitation and surface water into the soil. infiltration rate, often expressed as inches per hour, is going to be impacted by slope and surface shape, microtopography, and surface roughness. Any surface features that will slow down the water and hold the water is going to promote infiltration. Also, surface horizon characteristics that will promote absorption of this water will increase infiltration rate. Now, two of the soil factors that affect water infiltration and retention are porosity and bulk density. Soil pores are voids between soil solids that are filled with either air or water. Porosity is the percentage of the soil volume comprised of pores, and bulk density is the soil dry weight per unit volume. Your introductory soil textbooks often will present diagram A, which shows a soil where the volume is equally split between solids and pores. Now, this is a little misleading because we often find soils with very different porosities. You can have a soil like soil B or diagram B where 65% of the volume is pore space, or diagram C where only 35% of the soil volume is pore space. So which one has the capacity to retain more water? It's going to be B, of course, more pore space. So hydric soils absorb surface water and precipitation. They hold large quantities of water, and they transmit the water either to an aquifer or back to the surface. Why are they so good at these processes? Well, let's compare two items we should all be familiar with, a brick and a sponge. Brick has high bulk density, low pore space. A sponge, low bulk density, high porosity. So which one could clean up spilled water? Which one could hold more water? Which one would you choose to transfer water from the floor to the sink? The hydric soils with the highest capacity for water retention and transmittal are like sponges. Wetland degradation can result in a decrease in porosity and therefore a decrease in these hydrologic functions. Some wetlands hold the water due to a high bulk density subsurface layer. So in other words, we can find soils that are like sponges and some like bricks, sometimes within the same soil. Surface features that slow and hold water promote infiltration and water storage. Subsurface retention is going to be limited by the unsaturated pore volume, which is going to be determined by your soil thickness, depth to a confining layer, soil porosity, as well as the hydro period. This is a mineral soil flat, sometimes called winter wet woods, because they act as discharge systems during the winter. During the drier months, they act maybe as recharge systems. Because of their level condition, surface water retention is minimal. However, they tend to have deep soils, so below ground water retention may be high. That's going to depend on soil porosity, depth to a confining layer, and the hydro period. And here's a depressible wetland, in this case a Delmarva Bay. Because of its landscape position, these are surrounded by uplands. In concave surface, it has a high functional capacity for above ground water storage. Capacity for below ground water storage and groundwater recharge will depend on soil characteristics. Many of these have a confining layer within 2 feet of the soil surface. So not only is subsurface water storage limited, but there's also limited groundwater recharge. Here's the Piedmont slope wetland. It's driven by a backslope seep. Because of its slope, short-term water retention is limited. The water has a short residence time and quickly leaves the system as a first-order stream. Also, because of the hill slope position, these wetlands tend to have shallow soils. So there's little capacity for below-ground long-term water storage and groundwater recharge. However, they do function to maintain stream base flow. So I'll address some of the biogeochemical functions next. So these processes refer to processes that either change the chemical composition of a nutrient or pollutant, or spatially transfer these compounds. For example, the removal of phosphorus from a water column. And here's your second take-home message. The efficiency of wetlands in biogeochemical cycling is directly linked to the close proximity of aerobic and anaerobic zones and the cycles of wet and dry periods in hydric soils. Our first biogeochemical function is sedimentation, the removal of particulate matter from a water column. This is a relatively irreversible process that improves water quality by removing pollutants and pathogens adsorbed to the suspended solids, removing a source of turbidity, which increases light interception downstream, or light penetration downstream, and decreasing biochemical oxygen demand, or BOD. That's the quantity of oxygen required to decompose organic matter and oxidize inorganic compounds such as sulfides. Now, high BOD can lead to hypoxia. The downside of sedimentation is that it can ultimately degrade the wetland. Capacity for sedimentation is going to be dependent on geomorphic position and hydrodynamics. Depressional wetlands are more efficient than slope wetlands. Slow-moving water will release more sediment, high-velocity water. Soil organic matter accretion and soil carbon storage is governed by two processes: primary productivity, or carbon inputs, decomposition, or carbon losses. Wetlands typically have higher rates of primary productivity than uplands, therefore high carbon inputs. Periodic anaerobic conditions in hydric soils lowers decomposition rates, so they have low carbon outputs. So hydric soils typically have higher levels of organic matter than geographically associated upland soils. Soil carbon sequestration describes removal of atmospheric carbon dioxide and long-term storage of the carbon in soil. So carbon may be mineral, for example, carbonates, or organic, and soils are considered to be the largest carbon reservoir in the terrestrial carbon cycle. Carbon export is the loss of carbon from soil. There is atmospheric export, where carbon is lost as methane or carbon dioxide, as well as hydrologic export, the transport of particulate and dissolved organic matter down a hydrologic gradient. If it's being moved with surface water, it will support aquatic macroinvertebrate food chains. If it's driven by groundwater, that's going to promote redox processes for the biogeochemical functioning. Now, John addressed the cycling of redox sensitive elements. I will go over this quickly. So this molecular form of nitrogen, phosphorus, sulfur, and many metals is affected by soil chemical conditions and oxygen levels. Anaerobic conditions increase the solubility of phosphorus, iron, manganese, arsenic, copper, and nickel. It is the combination of aerobic and anaerobic conditions found in hydric soils that promotes the cycling of plant nutrients and the removal of pollutants from the water column. The primary pathways for nitrogen removal are plant assimilation and denitrification. Denitrification is the microbial conversion of nitrate to gaseous forms of nitrogen. Denitrification is dependent on organic carbon, which is supplied by root exudates as well as dissolved organic materials. Denitrification is promoted by alternating periods of aerobic and anaerobic conditions. Therefore, your seasonally saturated wetlands may be more efficient at removing nitrogen than permanently inundated wetlands. Now let's look at phosphorus removal. Note that there are many mechanisms for phosphorus removal, including sedimentation, plant and microbe assimilation, adsorption to iron and aluminum minerals in the soil by complexing with free iron and aluminum, hydrologic export, in particulate or dissolved form. In many cases, uplands or upland-wetland mosaics are better at removing phosphorus, and an upland buffer between wetlands and surface waters will increase phosphorus removal. So what role do hydrosoils play in functions pertaining to the food web and wildlife habitat? This is your third take-home message. By retaining water, large quantities of water, near the surface, you're developing anaerobiosis in the root zone. This is going to give a competitive advantage to shade-intolerant plants so that unique habitats will form in wetlands and unlikely to form in uplands. Other functional attributes of these hydrosoils are determined by the hydro period. When you have long-term inundation, this tends to promote open canopy wetlands and low bulk density soil, high in organic matter, which facilitates burrowing. For seasonal inundation, you get vernal pools, which are defined as seasonally inundated depressions that serve as nurseries for amphibians. Also, shallow water tables will promote tree throws, which will produce small vernal pools. Respective biogeochemical functions, these tend to support the aquatic macroinvertebrates, which are very important to both aquatic and terrestrial food chains. Hydrologic export of organic matter provides a food source for many of the aquatic macroinvertebrates. Removal of polluted water column is important in that many aquatic macroinvertebrates, like gilt snails and the larvae of mayflies and stoneflies, cannot tolerate polluted water. So to summarize, hydrosoils facilitate and regulate the flow of water between groundwater systems and surface water systems. Biogeochemical cycling is dependent on the combination of aerobic and anaerobic conditions in hydrosoils, and the capacity of hydrosoils to retain water and develop anaerobiosis promotes specific plant communities and unique wildlife habitats. I'll leave you with this thought. Many field observable soil features can be used as metrics in functional assessment of wetlands. That's a topic for another webinar.
Thank you so much, Bruce. We are thrilled that you were able to share all of that with us, and we'll take some time to digest all of that.